Okay, so the second speaker of this session is Shu Zhang from Germany. So let me briefly introduce her. So she has received her bachelor's degree from Tsinghua University, and she got PhD from Johns Hopkins University in 2019. After that, he worked as a postdoc researcher at UCLA, and since 2012-21, she is a distinguished PKS postdoc fellow in Max Planck Institute in PKS in Dresden, Germany. So she has been working on a variety of topics, including frustrated magnetism, such as quantum spin leakage, and also theoretical spintronics. In particular, recently she has very nice works on transport properties of topological materials. So today, I think she's going to talk about that. So let's welcome her with a big applause.
Thank you very much for the nice introduction. And I thank the organizers for inviting me to give a talk in this workshop. I'm a postdoc from Max Planck Institute of Physics of Complex Systems in Dresden, Germany. The talk I'm giving today is based on a work in collaboration with Mustafa G and my postdoc advisor Yaroslav at UCLA. And I'm sorry for my voice. I got sick from traveling recently. So if you cannot hear me clearly, please let me know. And I also apologize because I prepared for a short talk in my mind, and I didn't get time to change the slides much, but please feel free to interrupt if you have questions, and that might help me to fill the time. Okay, so this is the outline of my talk. Our motivation of this work is mainly to explore the interplay between real space and momentum space topologies. So I will give a brief introduction to what we have in mind about these two different types of topologies. And our main goal is to bias in injection of topological charges into a topological matter. So topological matter in the sense that the matter has momentum space topology, and it also has topological charges due to real space textures. And I will give two examples. One is the quantum Hall system, where topological charges are skyrmions, and it is a well-known topological matter. And the second example is a topological P plus IP superconductor, where the topological charges are the superconductor vortices with Majorana 0 modes. As we know, the topology is a ubiquitous phenomena. As Hassan said, emergent phenomena in topological physics are probably all around us, even in a piece of rock. The rock can be a magnet or quantum material nowadays. So for people working with band topologies, the more familiar type is probably the twisted band structures of electronic bits. And recently, there's the rising field of topological quantum chemistry, where people characterize all different types of band structures of all materials, and many more materials with topology, with non-trivial topology, came to our vision. And for people in magnets, the more familiar type of topology is probably magnetic defects, like skyrmions, as plotted here. Actually, this is more general than in magnets. because whenever you have an order parameter that is distributed in real space, their deformation as a form of excitation can be characterized as topological, trivial or non-trivial, and skyrmions are just one type of examples. So because topology is so generally existing, and it is very likely that this real space topology and momentum topology can coexist in one system. And when they coexist, they might interplay between each other. And I will give a few examples of systems where this happens. First example is a magnetic vase semimetal. So you have three-dimensional electronic bands where two wire cones are formed, and they're protected by topology. And because there is magnetic order in the system, for example, in this magnesium germanium or selenite, there can be 6 different types of domains. And when the 6 types of domains meet each other, they form a 6-fold vortex. And people have studied the density of states of electrons and as a function of their distribution in different magnetic domains and at the domain walls and the vortex. And as you can see in this plot, the density of state is is much higher at the vortex. Second example can be the topological superconductor. It is topological also due to electronic band structures, where you have 2 degenerate ground states that are equivalent and protected by topology. And now if you have a vortex, which is penetrated by a flux line, there can be Majorana 0 mode living inside this vortex. That's another example where the topological defect here is a superconductor vortex can affect whether or not the edge mode or boundary mode of a topological matter can show up. And the third example is bilayer graphene, where the order parameter now is the stacking of either A or B type of atom is on top of another atom in the bottom. So there are 2 types of equivalent ground state. And when they meet, they can form a domain wall. And on this domain wall, there can be an edge state, a helical edge state living there. So all these examples are where real space and momentum space topology can affect each other. And in this talk, we need to be more specific. So let me focus on a 2-dimensional topological matter, where the momentum space topology is given by the topology in electronic band structure. So like in the case before, but the real space topology is more specifically 2-dimensional ones that are defined by their quantized topological number, and more specifically, they're particle-like. So for example, skyrmions and vortices etc. So, and let's imagine when an external bias is acted on the edge state. What happens to the interplay between the edge state and topological charges in the bulk? So in the rest of this talk, I will explain to you that this bias, this edge state can perform as an interconnect where external bias act on through it to the bulk charges so that it assists in injection of topological charges. And why are we so obsessed with injecting topological charges? And as very well summarized by our last speaker, because topological charges follow topological conservation law, they're very stable in the bulk. So once they're injected to the from the boundary into the bulk, they cannot go anywhere. They're protected and they cannot annihilate easily. So it was proposed that they can be used as database in the future, like the racetrack memory shown by our last speaker. Moreover, if there is a way to bias the injection and ejection at the boundaries, we can build a circuit-like theory with chemical potentials at the boundaries and maybe some resistance in the bulk. And it almost looked like a battery and circuit type of theory. And then even for insulators, where there is absent of electron transport, you can still use topological charges as information carriers to go through insulators. So these are all very promising for spintronic applications. Moreover, for like vortices carrying Majorana 0 modes, this type of setup can be used to harvest in a current of Majoranas, which might be also promising for quantum computing and other purposes. So let's first look at the basics of injection theory. Let's think of equilibrium for now, and thermal agitation of topological excitations in the bulk. So we can imagine the one topological charge that's sitting very close to an edge of material. It has a probability to nucleate with nucleation rate gamma, and also has a probability to escape this material. So with an escape rate gamma bar. So the total charge flux at the boundary into the material is J, which is equal to gamma minus the density of topological charges times the escape rate. And in equilibrium, there shouldn't be any flux. So the total flux is 0. And we get a charge, equilibrium charge density, which is equal to a nucleation rate divided by the escape rate. On the other hand, we also know that the equilibrium charge density is given by the Boltzmann factor exponential to the minus beta times the energy cost per topological charge. And you can imagine in the reaction theory with an energy barrier, So the difference between the final state and the initial state is the energy cost for injecting one topological charge. And now if we suppose the nucleation is accompanied by a work, we don't know where the work is coming from for now, but let's just imagine if accompanying the nucleation of every topological charge, there is something that does work to the system. And then you can define effective local chemical potential, which is the work done to the system per topological charge. And in this way, we effectively tilt this energy barrier so that the energy needed to excite one topological charge is reduced by this chemical potential. And due to this renormalization, there is an enhancement of the ratio between the nucleation rate and escape rate, which actually gives rise to our familiar fugacity factor of the, if you can think of the topological charge as a gas system. And as a result, there is a finite injection flux now. And in the linear response regime, this is proportional to this chemical potential we define from the work. And so there has been some proposals of where this work can come from. In this paper by Ochoa and Sekwan and Yaroslav, they have a magnetic insulator as the host for skyrmions. And they attach metal contact to the boundaries of the magnetic insulator. And when you have electric current going through the metal contact, it can act as a spin transfer torque onto the dynamics of the magnetization in the magnetic insulator. And this torque is proportionate to the magnitude of the electric current and the spatial gradient of the magnetic order parameter. And then you can calculate a work done by the torque on the dynamics, so time derivative of the magnetic order parameter. And this work is then proportional to the integration of Skyrmion current density, which gives rise to the total number of injected Skyrmions, and is also proportional to the electric current density and going through the metal contact. Here we going to topological matter. Let's think about familiar quantum Hall system, where we can see some analogy between this case and the Skyrmion injection by electric current. So let's think about integer quantum Hall with filling factor 1. And as we all know, the bulk is an insulator, but it has a gapless and thus conductive edge state going around it. And when the Zima energy is smaller than the long-range Coulomb interaction between electrons, the bulk is literally a ferromagnet. So if you have a very strong magnetic field, all electrons are polarized. So the excitation is flipping one spin, and that is a quasi-particle excitation. But when the Zima energy is very small and the system is ferromagnet, the excitation, the lowest charged excitation is actually a skyrmion. So exactly like the ferromagnet case. Of course, you can have neutral excitations as spin waves, but the lowest charged excitations are skyrmions. And now we can put these coefficients in more strict forms. So the spin transfer torque here is again provided by the electric current on the boundary onto the magnetization dynamics. So the coefficient here is h bar over 2e, which means when you shoot in an unpolarized electric current, because the bulk is fully polarized, half of the electron spins will be flipped, and each flip contributes an h bar. So that contributes to this coefficient of the spin transfer torque as h bar over 2e. So again, it's proportional to the electric current carried by the edge state and the real space gradient of the magnetization. And now the work can be written in an exact form, which is h over e times the electric current, and again times the number of skyrmions injected into the system. And because we know the Hall conductivity, which gives the proportionality between the voltage at this edge and the electric current, we can plug this current in. And the work is exactly electric charge times the voltage. So what we were looking for in the beginning is a chemical potential for skyrmion injection. And what we find is actually a chemical potential for the charge. So by biasing the edge, we get a chemical potential for skyrmion equal to electric charge. And this is exactly what we expected, because skyrmions carry charge excitations in this system. And now on the other end, on the other boundary of the system, the injected skyrmions will hit this boundary, and they're free to escape the system. And we have the unstable reciprocity, which states that if you have a electric current at one boundary that can generate a voltage for the skyrmions, reciprocally, when you have a current of skyrmions, you can generate a voltage for electric charges. And that's why we have an electromotive force at this boundary, which is written in this form. And this gives rise to a current. So this is simply electric motive force divided times the Hall conductivity again. And this gives electric charge times the escape rate of skyrmions. So you can see this leakage comes from a longitudinal skyrmion current across the system, which also carries electric charge. So this actually might be one contribution to the breakdown of quantum Hall effect at large voltage or high temperature, because these skyrmion are injected by this edge current, and it can carry the charge longitudinally across the system. So for this familiar example, everything works out, and we get a quite general picture of the interplay between topological charges and the edge state coming from the edge bulk correspondence of momentum space topology. But not all edge states are charged. So in some cases, we can rely on a voltage to bias our edges. So let's imagine for charge neutral edge states, actually a more general scheme is to use thermal effects. And if we connect the edge to a thermal reservoir, because the edge is gapless, it will quickly equilibrate with the thermal reservoir, but not the bulk. So there might be an entropy or heat effect that can play a similar role as the work in our last example. So for this, we consider a topological P plus IP superconductor, where the topological charges are vortices, and the edge state is the Majorana mode. So in this figure, I'm showing two plots, one with on the left without vortex, and on the right with a vortex. So for these two considerations, the dispersion of the Majorana modes are exactly the same, but by threading a flux into the vortex, the boundary condition changes from antiperiodic for fermionic system to periodic due to the existence of this flux. So the discrete states on this dispersion are shifted, and we get exactly degenerate Majorana zero mode. And because the energy level difference omega zero between these discrete states are very small, because typically the Fermi energy E sub F here is very large. For the chiral modes on the boundaries, we can think of it as a continuous chiral mode, but because the vortices are small, these mini levels are more separated, as shown in this plot here. To think about vortex injection, let's assume that the bulk temperature is very low, and the edge is slightly heated up with TR, and both temperatures are much smaller than the mini gap of the Majorana zero modes at the vortex cores. So we can think of only the lowest energy levels in the vortices, and these are all much smaller than the superconducting gap. So we are very deep in the superconducting phase, and we don't have to consider the Bogoliubov excitation, the quasi-particles, and other things. To think about the adiabatic injection of a vortex into the system, we can compare two length scales. One is the distance between the vortex and the edge mode, and the other is the coherence length of the superconductor, which also defines the size of these vortices. So when the vortex is close to the edge, D comparable with the coherence length, the vortex, the Majorana mode inside the vortex and the Majorana edge mode will hybridize and split. So we have two different energy levels, but when they're far away apart, they don't feel each other. So we have two degenerate Majorana zero modes. And then this change from this injection process, separating the vortex from the edge, gives an entropy transfer from into the system. And this can be we can make the analogy of the situation to demagnetizing cooling to think about the entropy transfer. When you have a spin 1/2 system inside an infinitely large magnetic field, spin up and spin down states are separated. So the ground state is unique. But when you take away the magnetic field, spin up and spin down become degenerate, and the entropy is exactly the entropy of 1 qubit. So in this way, there is an entropy transfer or a heat transfer from this spin 1/2 and the system nearby, and that's how people have achieved demagnetization cooling. So very similarly here, by injecting a Majorana vortex into the system, there must be an entropy transfer. And we can put this into a more precise form by considering an impurity model of a adiabatic injection, where a Majorana zero mode vortex is sitting next to a chiral Majorana mode with linear dispersion. And with the linear dispersion in 1 dimension, the density of state is a constant. And we consider the hopping between this zero mode and this chiral mode with constant density of states. And this, when there's finite hopping between the two, we will get a broadening of the Majorana zero mode state, which has the density of state of the Bright-Wigner form. And you can see this is also a Lorentzian form where the broadening is given by capital gamma, which is proportional to the density of state of this chiral linear mode and the square of the hopping amplitude. So with this density of state, we can calculate the free energy of the Majorana zero mode. And because it's a Majorana mode, we only integrate over the positive energies from 0 to infinity. And nu here is the density of state, and this log term comes from the fermionic statistics of the Majorana zero mode. And the free energy gives us entropy carried by the vortex. And we can see when the hopping is very large, which means the vortex is close to the edge, the entropy is 0. But when the vortex goes deeply into the bulk and separated from the edge, we get 1/2 of kb log 2, which is actually the universal fractional entropy of a Majorana zero mode, as discussed in these papers. So now, instead of work accompanying topological charge injection, we can consider an entropy transfer accompanying the injection. And in this case of topological superconductor, the entropy transfer is exactly 1/2 of kb log 2. And similar to the role of chemical potential, this provides assistance to the free energy that's needed for the injection. And the free energy is corrected by the temperature difference between the edge of the and the bulk times this entropy transfer. And similarly, we get enhancement of the nucleation rate. So it's a nucleation rate divided by the escape rate is now enhanced by this exponential to the beta times temperature difference times the entropy transfer. And this is consistent with the entropy compensation rule in the reaction theory. And this might also provide a route to measure the universal entropy of a Majorana zero mode. if we plot the log of this ratio versus the log of temperature difference divided by temperature, so this temperature comes from this beta factor and the Boltzmann factor, the slope of this relationship will be exactly 1/2 log 2. Right? If this ratio can be, if this slope can be measured experimentally, this might provide a fingerprint for the existence of Majorana zero mode in vortices. Okay, so usually when we talk about topological matter, we tend to think of the edge mode as completely, like perfectly dissipationless. But actually here we explore the aspect of what happens if it's dissipative, and actually there might be some functional application of that by using this dissipation to do work or transfer heat into the system to assist the injection of topological charges. And because these bulk excitations are topological, these work or entropy injected is quantized. And with a definite quantity of these work and entropy, they might provide a route to manipulate or control how much, how many you inject. So this might be useful for spintronic applications. But we have to be careful that this quantization is in the mesoscopic sense, because it's quantized by average, because we have to think about the fluctuations between each injection processes. And fortunately, our approach, as I discussed in the last two examples, still apply when we consider noise or fluctuations of injection processes, because there is the Yardzensky equality that instead of considering the average of free energy, we can consider the average of the exponential of the free energy. And according to Yardzensky, this average still applies when we consider fluctuations of different and realizations of this injection. But we haven't considered some other non-universal effects in this process. For example, there can be impurities that change the energy barrier of injection, or in superconductors, the sample geometry might also matter. And there are dynamical effects such as spectral flow as the vortex move across the bulk with some final velocity. So it's important to think about adiabatic injection where this velocity is small enough so we can neglect dynamical effects. And the gas of topological charges inside the bulk has to be not so dense so that we can ignore the interactions between different vortices or skyrmions. Okay, so here's the conclusion of my talk. We consider the interplay between the real space and the momentum space topology. And the real space topology has the effect of giving these topological charges as defined by their topological numbers. And the momentum space topology gives rise to edge states. So we explore the functionality of this edge state as assisting the injection of topological charges, either by acting a work on the system or transferring heat into the system. And if you're interested in knowing about the details, you can read our paper here. Okay, thank you very much. And that's all.
Yep, thank you very much for the nice talk. Yep, any questions from audience? Yep. So yeah, I have a question. I have a question about this quantum Hall case. So in this quantum Hall case, skyrmion has this electric charge, right? When we bias when you bias this quantum Hall edge with the electrical voltage, wouldn't there be any effects, additional effects on these charged skyrmions due to electric charge? Would there be any, for example, yeah, for example, if we apply electric field to this edge mode, then this charged skyrmion will be pushed in the opposite direction to the electric field, right?
You mean electric field inside the plane, inside the quantum Hall plane?
Yeah, in plane. Yeah, in plane.
I think this is effectively acting. So there is a voltage on one edge and no voltage on the other
There's
edge.
ground.
So yes, the horizontal direction is the longitudinal direction for applying electric field.
I see.
In the perfect quantum Hall plateau, there should be only transverse current, right, at one edge and the other edge is zero. But because of the skyrmion excitation here, there is a leakage along the direction of electric field.
Also, yeah, another question about this Majorana case. Majorana case. So this, so would there be any non-local effect on this other side? What would be the effect on the other side?
Yeah, I didn't talk about it, but yes, there should be also the Onsager reciprocity.
Yeah, is it just a temperature increase on that side?
I think the idea is both edges should be connected to a thermal reservoir.
Oh,
so to keep a balance, to keep a difference between the two.
Oh, I see.
We are focused on the injection here.
I see. So you have a higher thermal reservoir with higher temperature on the left and the lower temperature on the right.
Yeah. I
see. Okay. Okay. Yeah. Thanks. And then there are some questions. Professor Hyung-Sun Choi.
Oh, thank you for an interesting talk. So here it seems like you're assuming the infinite dimension along the two parallel edges. So for example, the Majorana case, for actually a realistic sample, there would be a finite edge on these sides also, which would also, if you try to heat it up, the edge state can carry entropy along these boundaries on these sides, right?
Yes.
So
yes.
how that finite size affect the injection of the vortices in this case? If you
Yeah, thank you for the very good question. Yeah, I'll have to be more realistic with this. Yeah, so maybe the first is when I answer Sequan's question in the real setup, both edges, so the other two edges are applied with some temperature sink. And then when the vortex travel through the bulk, they might also travel transversely. So they can hit those edges you drew a minute before. So the skyrmions might also hit the finite edges, and yeah, that can also either raise the temperature of those edges, or the vortices might accumulate there and cause a different chemical potential. So I guess maybe in experiment there is a time window that we have to make sure that this the velocity of the vortex, the transverse velocity of the vortex is not too large, and when and the sample in the transverse direction has to be large enough that the vortex doesn't hit those edges very quickly. So maybe inside this time window is still okay.
Okay. Thank you.
Yeah, sorry, maybe it's not very practical.
It was an
Professor
experimentalist question.
Fair question.
Thank you very much for your talk. So I have one question about the analogy you're making between quantum Hall case and the chiral topological superconductor case. I mean, in case of quantum Hall, I suppose, I mean, we can pretty much assume that, you know, just by our voltage bias, we are actually getting the same sign of our skyrmion. Our skyrmions are the same sign for most practical purposes, and that would place some limit on what kind of interaction we should expect between these topological defects when we start to inject in more of them. But I mean, can we say something similar about chiral topological superconductor? Because I'm not really sure whether, you know, when we're increasing this temperature difference between two edges, I'm just not sure whether we can, that would mean that, say, like we would have same vorticity. You're sure to inject in vortices with same vorticity. I mean, this kind of analogy, I'm not sure we can really, I mean, is there any argument for this, or I mean, do you think there's no such analogy between quantum Hall and P plus IP superconductor?
Are you saying it's like difficult to separate this injection effect from other thermal effects?
No, what I'm saying is that at least in quantum Hall case, I mean, you were worried that once we start to inject in lots of topological defect, interaction between them might become important.
Yes.
But in the case of quantum Hall, I mean, basically we are injecting in skyrmions of same sign.
Yes.
So that kind of places restriction on the interaction between them. I'm just wondering whether you can say something analogous about in P plus IP superconductor, or I mean, these two cases are completely different in that regard.
They are similar in the sense that the vortices also interact, right? And here we assume there's only one species of vortex, so only the so that they don't annihilate with each other. This might require some out of plane magnetic field to give the preference between plus or minus one vortices. And then when two vortices get close to each other, there is a similar effect of hybridization that Majorana can hop between vortices, and that's an interaction effect we didn't account for.
I see. So in other words, annihilation between pair of vortices is something we need to worry about in P plus IP superconductor that we didn't need to worry about in for quantum
Yes,
mode case.
yes, that's correct.
Okay. Thank you very much.
Thank you.
Okay, if there's any further question, let's thank the speakers of today's sessions, or the today's session, yes, today's